For someone who rejects the concept of infinity, it would appear that the mathematics of infinity has corrupted science. Say we discover that 1 in 30 darts thrown at a dartboard bounces out. This figure simply describes a numeric part of the effect. It doesn't tell us the cause of the effect. And that is exactly what mathematics does in science. It describes numeric parts of an effect. It doesn't tell us what caused the effect. Should the scientific approach be to claim the effect of a dart bouncing out of a board is beyond all human comprehension, and so we should just accept the maths? Or would that be the complete opposite of scientific? But this is often the position of our academics. They tell us we should accept there are things beyond our understanding, and if the maths works, then that's all that matters. And if we don't think that the maths provides clarity, then we're probably just not clever enough to get our heads around it. Many scientific theories can supposedly only be described using mathematics. Surely we shouldn't reject something like quantum mechanics just because we don't understand it, should we? Normally, we would concede to the superior knowledge of the academic experts. But perhaps we should fight back for once. Perhaps we shouldn't accept that something is beyond human understanding. Otherwise, we might be tempted to accept the supernatural instead of trying to find a real-world explanation. For us, the maths alone is not enough. We want a proper explanation. And perhaps we should reject quantum mechanics if it really doesn't make any sense. Yes, it might well be true that there are things that are beyond what we perceive to be our physical world. For example, we might all just be intelligent characters in a computer game being played by a greater intelligence. In such a scenario, our physical reality is restricted to things inside the game. We would have no access to the place beyond our reality. We would have no way of knowing that a greater intelligence was influencing or controlling events inside our reality. So yes, it is possible that there might be things that we can never understand. But we should never accept that there are. To do so would allow us to abandon scientific investigation. Once we start to accept that an effect was caused by forces from a realm beyond our world, we will have abandoned the scientific approach in favour of a faith-based belief system. It might be very desirable to believe in things that can never be backed up by empirical evidence, such as there being infinitely many versions of the world, and in many of them everything went right for you. Such theories should not be called scientific, and yet scientists are the ones saying these things. It makes science appear to be a ridiculous and farcical subject. And should the only test of how good a theory be its ability to make good predictions? If we claim that a large invisible space cat makes the sun rise every day, then it might make good predictions, but it's obviously a load of nonsense. In addition to making good predictions, a good theory should provide a greater clarity of understanding, and ideally all aspects of a theory should be supported by empirical evidence. We might invent a theory that says, in order to travel from A to B, we need to complete an infinite number of journeys. But this is not a good theory, because instead of providing a greater clarity of understanding, it creates more confusion with its strange notion of completing an infinite amount of journeys. There's a weird notion that rather than being man-made, mathematics is some mystical language of the universe that we have discovered. Not only that, but it can say things about the natural world that can't be expressed using natural language. This is bizarre. The symbols used in mathematics all have natural language meanings, and so the symbols are just a form of shorthand. The real problem is that some of these natural language meanings have no tangible mapping to physical reality. For example, instead of a mathematical length mapping to a real-world measurable distance, it is claimed to be an infinitely thin extent between two infinitely small points in multidimensional space. We can't sum to infinity in the real world, and there are no physical distances corresponding to pi or the square root of 2, just finite multiples of Planck lengths. This doesn't mean we should completely abandon pi and the square root of 2, it just means that they can't be static lengths, and so we should treat them as something else, such as process-related functions. Sadly, the world of science has accepted the weird notions of mathematics even though they make no sense in physical reality. One example of how maths has corrupted science is the slippery notion of multiple spatial dimensions. We are given a story that goes something like this. If we keep zooming in on a flat, apparently two-dimensional object, then eventually we'll see that it's really three-dimensional. We are then expected to believe that by similar logic, even more dimensions might exist that we can't see. But the word dimension traditionally means a measurement of a defined length. So if I measure my foot, leg, waist and chest, then these are 4 dimensions. This concept of dimension has been corrupted by the mathematics of infinity. In mathematics, points in space are infinitely small, and each point can be described by 3 numbers called its x, y and z coordinates. And this is where the idea of 3-dimensional space comes from. But if the real world doesn't consist of infinitely small points, then the whole basis of spatial dimensions is flawed. It means there's not 3 spatial dimensions in physical reality. There's just space. And the zooming in logic that supposedly leads to the possibility of more spatial dimensions that we can't see does not apply. It is highly unlikely that the smallest parts of space are arranged in a nice layout that is easy to model mathematically. But as we don't know how they're arranged, we might as well model them as though they are boxes. Then 3 perpendicular measurements from an origin will uniquely identify any given position. But we could devise a strategy for assigning a unique number to each box. This would allow us to describe any position with just one number. It doesn't matter how many numbers we use to identify a position in space. There's no reason to believe that things might exist in extra spatial dimensions that are beyond our abilities of perception. Yes, we can devise mathematical expressions in which we have more than 3 variables to represent so-called spatial dimensions. But made-up mathematics doesn't tell us about the real world. Maths should be based on physics, rather than physics being based on maths. It is often claimed that only the language of mathematics will allow us to understand various scientific phenomena, such as the weird quantum wave, that is described in terms of probability distribution. But does a mathematical expression really provide an explanation? Newton's equation for calculating the gravitational force between 2 bodies doesn't provide any explanation about what mechanism produces the force that we call gravity. And in order to understand any mathematical symbol, it has to have a meaning in a natural language. On this basis, there isn't any independent language of mathematics. So why are we trying to describe physical things in terms of maths? And where did the notion of quantum weirdness come from in the first place? Well, it came from the study of small particles, especially the study of the nature of light. The ancient Greek philosopher Democritus argued that everything must consist of smallest parts, even light. Considered the father of modern science, Democritus was trying to explain physical phenomena in terms of simple fundamental concepts. Thomas Young's double-slit experiment in 1801 promoted the idea that light might be a wave. But in 1905, Einstein postulated that light might consist of particles called photons. Then in the mid-1920s, quantum mechanics was devised, in which it was postulated that every quantum entity can act as either a wave or a particle. But other waves in nature can be described as an oscillation of particles in a medium. So our only understanding of a wave is something that is particle-based. Could empty space be a particle-based medium that somehow gives light its wave nature? The medium of empty space was called ether, and in the 17th century Robert Boyle, best known for Boyle's law, proposed that one or two particle-based ethers might help to explain phenomena such as magnetism and gravity. A few years later, in 1687, Isaac Newton described ether as a medium that flows continually downwards towards the Earth's surface, and he talked about an ether density gradient. Could Newton have been right about ether being the cause of gravity? Well, Newton's cradle appears to indicate that energy is conserved when travelling at constant velocity. And since we consider energy and mass to be essentially the same thing, then perhaps mass can move through space at constant velocity without losing energy. In which case, perhaps we only feel the effect of ether when matter or energy is accelerating or decelerating through it. And perhaps parts of space can somehow be randomly created and depleted. Or perhaps matter can transform into space, and vice versa, and maybe these things can pop into and out of existence. And if we suppose that more space tends to be depleted than created where mass is plentiful, then this would cause a steady flow of ether towards the Earth's surface. The ether would speed up as it approaches the Earth's surface because the available volume for it would be reducing. This would result in a constant downward acceleration of ether, which could conceivably create the force we call gravity. A theory of ether, where ether is created where mass is sparse and depleted where mass is plentiful, could be an extra tool that might be useful for explaining other phenomena such as dark energy, dark matter, and possibly other things. Sadly, Newton discarded his theory of ether and used mathematics to describe the effect of gravity without providing a mechanical explanation of what causes gravity. But it was still hypothesized that light was a wave and propagated through an ether. And instead of being a downward force, it was thought that ether would cause a sideways wind-like force on light. Such a sideways force was ruled out by the Michelson-Morley experiment in 1887, and inexplicably many people concluded that ether could not possibly exist. There's an obvious similarity between Einstein's idea that gravity distorts space and Newton's idea of a downward flow of ether forming a density gradient. They both predict that gravity should affect light. If light doesn't propagate through a medium, then how can we explain its wave-like nature? And should we be happy to have only mathematical descriptions for gravity and quantum waves? Instead of just maths, shouldn't we want more tangible theories about the underlying mechanisms behind these effects? If maths alone is insufficient, then we would have to admit that when we talk about something like a quantum wave of probability, we don't really have a clue what we are talking about. Sound propagates through air in spherical waves of pressure. And we have a formula for the amplitude or displacement of particles from their mean position at any given distance. But we know that sound doesn't persist forever, as the mathematical formula suggests. Also, the amplitude doesn't tend towards infinity as we get close to the source, as the mathematical formula suggests. So we can't trust the maths, even though it appears to work in most cases. The maths doesn't properly reflect the finite and granular nature of physical reality. This highlights the problem of claiming that something can only be described by mathematics. The expression A over R tells us that the amplitude decreases as distance increases. But it doesn't explain the physics involved. It doesn't explain why the amplitude decreases. It tells us nothing about the physics of the molecules that cause the effect. Sadly, nowadays, physicists often claim that a particular phenomenon is explained by some mathematical expression. Perhaps it's time for physicists to stop doing this. Even with a theory of parts of space, it is not easy to explain the result of the double-slit experiment. But without any ether, we've got very little to work with. We might, if we were advocates of quantum mechanics, resort to proposing that small particles can somehow choose between acting as a mysterious wave of probability and acting as a particle. And since a single slit appears to result in particle-like nature, we might propose that the particle or wave decision depends on whether or not the result would allow someone to be able to determine which slit it went through. But if a decision is being made, then who or what makes the decision? Are we all subservient to some higher intelligence? It's all very strange. An even weirder inevitability that emerged from quantum theory was that two particles at different physical locations must be able to act as a single entity. These particles were said to be entangled. For several decades, nobody could think of a way to test if entanglement was really happening. Then in 1964, John Bell outlined a test that could be done using the mathematical concept now known as a Bell inequality. And in 1972, the first Bell test was performed. But the large number of missed detections meant that not only was a classical physics explanation possible, but it might have been better at predicting the result. Quantum mechanics doesn't require there to be any missed detections, but a classical physics solution would predict a certain amount of missed detections. They are required in order for a classical physics solution to significantly violate a Bell inequality. But any explanations based on classical physics were sidelined as possible loopholes, and the weirdness of quantum mechanics became widely accepted by physicists. Many Bell test experiments have now been performed, several of which have claimed to be loophole-free, but all of them can easily be contested. And so we still don't have a single definitive experiment that proves beyond all reasonable doubt that spooky quantum entanglement really exists. If we had a definitive experiment, then every aspect of it could be scrutinized in depth. Physical aspects of the experiment could be altered to see what effect it had on the overall outcome. This drilling down into the detail might well indicate a possible classical physics solution. If the advocates of quantum mechanics are right, then they have nothing to fear from such intense scrutiny. They might have nothing to fear, but they would have a lot to lose. Quantum mechanics is currently accepted by mainstream physicists. But this could change if we had a definitive experiment that was debunked. They would much prefer the current situation, where many experiments are described using the terminology of quantum mechanics, in which it is already assumed that a choice is being made about when a wave collapses into particles. This can lead to some very bizarre conclusions. The delayed choice quantum eraser experiment includes a delayed choice of path achieved by changing the apparatus while the photons are in mid-flight. From the resulting patterns on the detection screens, it is deduced that the photons must have somehow reversed their earlier decision as to whether to act as a wave or a particle? How can the decision to pass through a double slit as a wave or a particle be made after it's passed through the double slit? Surely such an explanation is absurd. Wouldn't it make a lot more sense to take into account undetected photons instead of ignoring them, so that a classical physics explanation becomes plausible? But no, the accepted explanation is bewildering. They think that they can really change events that occurred in the past. If something sounds too ridiculous to be true, it probably is. Who is going to believe that scientists can change the past? There's very little for the disbeliever to do here, because the scientists' over-the-top claims are just not believable.